Hello there, and welcome to sleepy ancient Earth. Tonight, we drift back before oceans, before continents, before the first hint of life. We travel to the Hadean, Earth's first world, and its strangest. The Hadean was not quite a planet yet, not quite the molten cloud it came from, but something in between. A world still deciding what it would be. It began about 4,540,000,000 years ago, and it earns its name from Hades, fitting for a place built from fire. Some of it formed in a rain of colliding rock that built a planet in a few million years. Some of it glowed as an ocean of molten stone with no solid ground anywhere. Others speak of a Mars-sized world called Theia, striking the young Earth and leaving behind a moon. While through it all, a sky with no ozone let raw light fall on a surface that had no one to feel it. If you enjoy these quiet journeys into the deep past, feel free to like and subscribe or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, let's begin. The Hadean Eon began about 4,540,000,000 years ago. This marks the very start of Earth's geological record, long before any rock we can still hold in hand existed to preserve it. Scientists trace this beginning from the oldest surviving fragments of the solar system, tiny grains of zircon and stray meteorites that crystallized in that first fire. The date is not a single instant of birth, but an average drawn from scattered clues, since nothing continuous survives from so early a time. Still, everything that followed, the oceans, the continents, the first breath of life, rests on this foundation. Human memory reaches back a few thousand years. This one eon alone lasted longer than all of animal life that would ever follow it. To hold that number in mind for a moment is to feel time stretch past any scale a single life can measure. It is where the story of this world quietly begins. It marks Earth's first chapter, before oceans, continents, or life existed. At this stage, the planet was barely a planet at all, still finding the shape it would keep for billions of years afterward. No crust older than about 4,400,000,000 years has ever been found, and everything before that has simply vanished into the churn of that early world. This does not mean nothing happened during those first 100,000,000 years, only that no record of it survived to reach us. Yet the chemistry set in motion then, the mix of elements pulled together from the solar system's leftover dust, shaped every ocean and every living thing that would come later. The stable, quiet continents we know today were not the rule in this early history. They were the exception, still ages of change away. To stand on such a surface, if standing were even possible, would be to stand on a world still being decided. Nothing there yet knew what it would become. The name comes from Hades, fitting for a molten, violent world. Geologists borrowed the name from the Greek god of the underworld, a fitting choice for an age, with no sky to speak of and no ground that stayed still. In places, the surface likely glowed above 1,200 degrees Celsius, hot enough to keep whole regions in a state of liquid rock. This was not a hell in the mythic sense. No punishment, no judgment, only heat and endless motion. That heat kept the planet from settling into any lasting shape for tens of millions of years. Not a solid world, not quite a star, but something caught between the two, glowing faintly in the dark of a young solar system. Picture a lantern with no one to hold it, burning simply because burning was what it did. It was fire without witness, and it lasted a long while. Earth formed from dust and rock swirling around the infant sun. Around 4,600,000,000 years ago, the solar system was little more than a spinning disk of gas and grit, circling a star that had only just begun to shine. Astronomers call this disk the solar nebula, and it likely stretched far beyond where the outer planets now orbit. Nothing about this process was quick or clean. Tiny grains stuck together into pebbles, and pebbles into boulders, over what may have been hundreds of thousands of years. Gravity then took over, pulling these clumps into larger bodies as their paths crossed again and again. The calm, fixed orbits of today's solar system give little hint of how disorderly that early swirl once was. Earth's beginning had no single edge, only a gradual gathering of debris drawn slowly inward. It was less a birth than an accumulation, patient beyond any human measure. A world built one collision at a time. Countless smaller bodies collided and merged to build the growing planet. During this violent infancy, Earth grew not by any plan, but by addition, one impact at a time. Some of the objects that struck it were the size of small moons, tens of kilometers wide. And evidence suggests the young Earth absorbed thousands of such collisions before its surface ever cooled. This was not chaos without pattern. Gravity organized the process, drawing larger bodies toward each other faster than small ones, so that growth accelerated as the planet gained mass. Each strike added not only rock, but heat, driving the temperature of the interior higher with every collision. A single meteor shower today might scatter a few visible streaks across a night sky. The Hadean Earth endured that kind of bombardment without pause, for millions of years at a stretch. There was no calm between the impacts, only the next one arriving. The planet was, in a sense, built from its own bruises. This process, called accretion, took only a few million years to complete. Astronomers estimate that within about 10 to 20 million years, Earth had already gathered most of the mass it would ever hold. Compared to the 4.5 billion years the planet has existed since, this was barely an instant. A rapid assembly finished almost as soon as it began. Quick is a relative word here. 10 million years is longer than any structure humans have built has stood. Yet against the life of the sun, it barely registers. Once the bulk of the planet had formed, the bombardment did not stop, but it slowed, scattering smaller impacts across the ages that followed, rather than the constant crush of the earliest years. Imagine a planet reaching nearly its full size before it had even finished cooling, still glowing, still shifting, and already almost whole. What took so little time to build would take far longer to calm. The young Earth's surface was likely a churning ocean of molten rock. The heat from countless impacts, together with the decay of radioactive elements inside the planet, kept the outer layers liquid for millions of years. Geologists estimate this magma ocean may have reached several hundred kilometers deep in places. A molten layer, far thicker than any ocean of water that would follow it. No one has ever seen such a surface, of course. What we know comes from computer models and from the chemistry locked inside the oldest minerals that managed to survive from that time. Within this ocean of fire, heavier elements like iron sank slowly toward the center, while lighter material rose toward the top, sorting the planet into the layers it still holds today: a core, a mantle, and eventually a crust. The solid ground we now take for granted did not exist yet in any form. There was only heat, moving slowly downward and outward, deciding what would sink and what would rise. Nothing had a shape yet, only motion. Temperatures at the surface may have exceeded 1,000 degrees Celsius. This was the early Hadean, when the planet had barely finished gathering its mass and had nowhere yet to release the heat trapped within it. Estimates drawn from computer models and the physics of planetary formation place the surface heat at well over 1,000 degrees in the hottest regions. hot enough to keep rock in a liquid state rather than a solid one. No thermometer could have measured this, of course. The number comes from working backward through the energy of impacts and the slow decay of radioactive elements buried in the young Earth's interior. At such heat, nothing we would recognize as ground could exist. Only a shifting skin of fire stretched across a planet still finding its shape. The hottest deserts on Earth today reach perhaps 50 degrees on their worst afternoons, a gap too large to hold in the mind at once. To imagine standing on that surface is to imagine standing nowhere at all, since nothing solid was there to stand on. Heat was the only ground the young Earth had. No solid crust could form while such extreme heat persisted. For as long as the surface stayed above the melting point of rock, there could be no lasting skin over the planet, no matter how many times a thin crust tried to knit itself together. Geologists suspect that any crust which did form in these early years lasted only moments before the heat beneath it melted it back into the churning mass. This may have continued for tens of millions of years, a stretch long enough that entire crusts could have formed and failed and formed again, without a single one surviving to the present day. The lack of evidence is itself a kind of evidence, since nothing from this period remains for scientists to study directly. Whether later Earth would grow a shell of rock thick enough to carry oceans and mountains, the Hadean world could not hold even a single layer in place. Nothing stayed still long enough to count as ground. Even stone, it seems, must wait its turn to become permanent. Roughly 100 million years in, a Mars-sized body struck Earth. By then the planet had cooled enough to hold something like a shape, though still far from calm, when this second world crossed its path and collided at tremendous speed. The impactor is thought to have been close to the size of Mars, roughly half the diameter of Earth itself, an object large enough to count as a planet in its own right, rather than a stray piece of rubble. No fossil or rock records this moment directly, since anything present at the time was reshaped by the very event we are describing. Such a collision would have released enough energy to melt both bodies again, undoing whatever solid ground had begun to gather. Imagine two young worlds, each already vast, meeting at speeds far beyond anything on Earth today, and neither surviving the meeting unchanged. Earth kept its name and most of its mass. The other world did not stay whole enough to keep its own. Scientists call this hypothetical body Theia, named for a Greek titan, said to be the mother of Selene, the goddess of the moon. The name was chosen deliberately, since the object is thought to be responsible for the moon's birth, and the old stories offered a fitting parent for such an outcome. No fragment of Theia has ever been found and identified with certainty, so the name refers to a body known only through its consequences rather than through any physical trace. Researchers reconstruct its probable size and composition by studying the chemistry of moon rocks and comparing them to Earth's own mantle, working out what kind of collision could have produced the mixture we see today. It is unusual in science to name something never observed directly, yet Theia has become a fixture of the story, spoken of almost as if it once had a place on a map. In a way, it did. That place simply no longer exists, since the world it named gave itself entirely to the making of another. The collision's debris is thought to have coalesced into the moon. In the aftermath of the impact, a vast ring of molten and vaporized rock is believed to have circled the wounded Earth, spread out along its equator like a bright band in the darkness. Models suggest that this material gathered itself into a single body within a few hundred years, a timescale almost impossibly short for the birth of a world nearly a quarter the size of Earth. What seems like a slow, gentle process from a distance was in truth a violent gathering, chunks of glowing rock pulling toward one another under their own weight until they formed a single sphere. The heat of this newborn moon would have kept it glowing for a long while afterward, a companion still cooling from its own creation, even as Earth continued cooling from its own. No ocean, no life, no witness watched this happen. The sky simply gained a second light, born from the wreckage of the first collision Earth ever fully remembers. This giant impact hypothesis remains the leading, though still debated, explanation. Other ideas have been proposed over the years, including the notion that the moon split directly from a fast-spinning Earth, or that it formed elsewhere and was later captured by Earth's gravity. Each of these alternatives struggles to explain certain details, particularly the close chemical match between moon rocks and Earth's mantle, a similarity the impact model explains more naturally than the others. Even so, the impact hypothesis carries its own unanswered questions, especially around exactly how much of the moon's material came from Theia rather than from Earth itself. We do not know the answer with certainty, and the record left in ancient rock can only narrow the possibilities rather than settle them outright. Scientists continue to test the idea against new samples and new models, refining rather than replacing it. For now, it remains the story that fits the most evidence with the fewest contradictions. Certainty, in this case, is still a work in progress. The newborn moon orbited far closer to Earth than it does today. In those earliest years, it may have circled at a distance of only 20,000 kilometers, compared to the nearly 400,000 kilometers that separate the two worlds now. Tidal forces between the two bodies have been pushing the moon outward ever since, a slow drift of a few centimeters each year that has carried it to its present distance over billions of years. This closeness came with consequences beyond mere appearance. Earth's days were shorter then, its rotation faster, and the tides pulled by such a near companion would have been far more extreme than anything the oceans would later know. Imagine looking up into a Hadean sky and finding the moon several times larger than it appears now, close enough to make out shadows without any telescope at all. No one stood on that shore to see it, since oceans and shores were still ages away. The sky held its greatest wonder long before there was an eye to notice it. A day on early Earth may have lasted only 6 hours. In the planet's infancy, before the moon's pull began to slow it, Earth spun far faster than it does now. Calculations based on the planet's early rotation suggest a full day and night may have passed in as little as 6 hours. No clock stood on that spinning surface to confirm it, and the figure comes from working backward through the physics of momentum rather than from any direct measurement. Such rapid spin would have flattened the planet slightly at its middle and driven fierce winds around a world still glowing with heat. A person living through one of those days would have seen the sun cross the sky 4 times faster than it does today, sunrise and sunset following each other in a blur. To stand on that surface, had anyone been able to, would have meant watching an entire cycle of light and dark complete before a modern breakfast could finish. The planet was young, and it moved like something young, restless and quick. Tidal forces between Earth and Moon were far stronger than now. With no ocean yet to answer the Moon's pull, it was the rock and magma of the young planet itself that felt the tide. Some estimates suggest the ground could have risen and fallen by as much as 100 meters, with each pass of that nearby moon, compared with the meter or so an ocean tide lifts today. This was not water moving, but solid and molten crust flexing under gravity, a slower and heavier motion than any wave. The constant stretching added its own share of heat to a planet already glowing from its birth, kneading the crust the way hands might work dough. where today's tides are gentle enough to set a rhythm for tide pools and shorelines. Those early tides moved the ground itself. Picture a surface rising and settling in a slow, heavy breath, though no shoreline yet existed to mark the difference between high and low. The moon did not just glow above the earth, it needed it. Earth's interior began separating into core, mantle, and crust by density. In the planet's molten first tens of millions of years, gravity acted like a patient sieve on every element within it. This sorting, known as differentiation, unfolded gradually, though much of it may have been largely complete within the first 100 million years of Earth's existence. It was not a single moment, but a slow settling, heavier substances sinking, while lighter ones rose. The way sediment might settle in still water, only on the scale of an entire world. From this sorting came the three broad layers that still define the planet today. A metal core at the center, a thick, rocky mantle around it, and a thin crust at the surface. A cook stirring oil and water together would recognize the pattern, though on a scale no kitchen could hold. To picture the whole earth arranging itself by weight is to imagine a fire that had no hurry, sorting metal from stone across an age too long for counting. The planet built its own architecture. No hand guided it but gravity. Heavy iron and nickel sank inward to form the planet's core. Among all the elements swirling through the molten young earth, iron and nickel were heaviest, and heaviness has its own quiet momentum. Over time, these metals gathered and sank toward the center, forming a core that today measures roughly 3,400 kilometers in radius, larger than the entire planet Mars. The descent was not instant. Droplets of molten metal likely fell through the surrounding rock, much as rain falls through air, gathering into larger pools as they went. What settled at the center became the densest and heaviest part of the planet, a metal heart that would later do far more than simply anchor Earth's weight. The rock left behind, lighter and cooler by comparison, rose to become the mantle that surrounds that core to this day. Picture that fall, not as rain through open sky, but as rain moving through solid stone, each drop finding its way downward over millions of years, rather than minutes. The Earth's center is iron, because iron always finds the bottom. This differentiation released enormous heat, keeping the mantle partly molten. The sinking of iron and nickel was not a gentle settling, but a fall driven by gravity, and falling releases energy wherever it happens. Scientists estimate this process alone may have added several thousand degrees to the planet's internal temperature, on top of the heat left over from Earth's violent formation. This was not a passing surge, but a heat that lingered, since rock is a poor conductor and holds warmth far longer than it lets it escape. The added warmth kept much of the mantle soft and slow-moving, if not fully liquid, for hundreds of millions of years, feeding the volcanic activity that shaped the crust above it. A compost heap warms itself through decay on a small scale. The young Earth warmed itself through gravity on the scale of a planet. Picture that heat sealed deep within, not visible from any surface, quietly keeping the interior workable, like clay left too near a fire. The planet cooked itself from the inside, and it is, in some sense, cooking still. A magnetic field may have formed early, generated by the churning core. As the core took shape, its outer layers stayed liquid while its center firmed. And movement within that liquid metal can generate a field far beyond the reach of any single rock. Traces preserved in ancient zircon crystals suggest a magnetic field may have existed by 4,200,000,000 years ago, remarkably early in the planet's story. The record here is thin and difficult to read. and scientists remain uncertain how strong that early field was, or whether it held steady across those first ages. Whatever its strength, a magnetic field would have helped shield the young atmosphere from the sun's constant stream of charged particles, particles that might otherwise have stripped lighter gases away entirely. A compass needle today responds to a field born from that same churning motion, still turning quietly toward a process that began billions of years earlier. Picture invisible lines curving around a planet that had no life yet to protect. A shield built before there was anything it needed to shield. Protection came first. Purpose came later. The sun itself was fainter then, part of the faint, young sun paradox. The star at the center of the solar system was not yet the sun we know, and stars, like everything else, grow brighter as they age. Around 4 billion years ago, the sun likely burned at only 70% of its current brightness, a dimness that should have left Earth locked in ice by most straightforward calculations. Yet the geological record suggests liquid water and warmth persisted anyway. A contradiction scientists call the faint young sun paradox, one that has never been fully resolved. The likeliest explanation points to a thicker blanket of greenhouse gases, methane and carbon dioxide trapping heat that a dimmer sun could not provide on its own. Where a modern eye might expect a weaker sun to mean a frozen world, early Earth seems to have found another way to stay warm. Picture a paler sun hanging in a hazy sky, doing less work than it does now, while the planet beneath it found its own quiet ways to hold on to heat. The sun gave less. The Earth simply learned to keep more. Despite the dim sun, Earth's own heat kept its surface scorching. In these first hundreds of millions of years, warmth came less from the star above than from the planet's own restless interior. Heat left over from its violent formation, along with the steady decay of radioactive elements buried within the rock, kept temperatures in places above 1,000 degrees Celsius. This was not sunlight at work, but an inheritance, energy stored during the very collisions that had built the planet. That inheritance kept much of the crust molten long after a fainter sun alone could have managed it, slowing the world's cooling by hundreds of millions of years. Where a distant star offered little, the ground beneath gave everything it had stored. To stand on such a surface, if anyone could have, would be to feel heat rising through the soles of the feet before ever looking up at the sky. The warmth came from below, not above. The atmosphere, if it existed, was thin and unlike today's air. So many of the giant impacts that shaped this early world, around 4,400,000,000 years ago, carried enough force to blast away any gases the young planet had gathered. And some researchers wonder whether Earth's air was stripped and rebuilt more than once before it settled. What clung to the surface likely formed a thin haze, holding perhaps only a fraction of today's atmospheric pressure, far less substantial than the thick blanket of nitrogen and oxygen surrounding the planet now. Without enough weight in the sky above, heat could escape freely into space each night, and temperatures may have swung wildly between a scorched day and a frozen dark. Fossils of the sky do not exist, so what is known here comes from models and traces in ancient minerals rather than the air itself. Picture a thin veil overhead, offering little comfort and little protection, more suggestion than shelter. The sky itself was still deciding what it wanted to be. Volcanic outgassing likely released carbon dioxide, water vapor, and nitrogen into the sky above the young Earth. Across a crust dotted with restless vents and fissures, magma rising from below carried dissolved gases trapped since the planet's formation, and every eruption sent some of that trapped breath skyward. Estimates suggest carbon dioxide and water vapor dominated this exhaled air, with nitrogen present in smaller amounts, a mixture with almost nothing in common with the air filling a room today. None of it was breathable, and none of it needed to be, since nothing yet drew breath. Still, this constant volcanic exhale is thought to have built the first real atmosphere worth naming, thickening the thin haze into something with actual substance. Where a single volcano today might barely stir the air around it, thousands working together across a molten young world could shape an entire sky. Imagine standing where a fissure vents its gas into open air, watching the invisible become, slowly, an atmosphere. The world exhaled long before anything could inhale. There was no free oxygen anywhere in this early atmosphere, not a single breath's worth drifting through the sky. The gas that fills a fifth of today's air simply did not exist in loose form. Since nothing yet existed to produce it, and oxygen would not appear in any real quantity for another 2 billion years. What oxygen there was stayed locked inside water molecules and mineral rock, bound too tightly to circulate freely on its own. Iron that would rust orange within days on the surface today could sit exposed for ages in this world without a trace of that change, since rusting depends on oxygen being present to react. This absence shaped the chemistry of everything, from the rocks forming at the surface to whatever gases mixed above them. Human lungs, dropped into that air, would find nothing there to sustain them, only gases utterly indifferent to breath. The air asked nothing of anyone, because there was no one yet to ask. Ultraviolet radiation reached the surface unfiltered, with no ozone layer to soften its force. Ozone forms only where oxygen exists in the sky above, and since this early air held none, the shield that now protects every living thing from the sun's harsher rays had not yet come to be. Sunlight fell directly onto exposed rock, and standing water carrying nearly its full strength, energy that today's ozone layer filters out, absorbing well over 90% of incoming ultraviolet radiation before it ever reaches the ground. Rather than only harm, some scientists suspect this raw radiation may have helped drive the chemistry that eventually built the first organic molecules, breaking bonds and rearranging atoms into new and useful shapes. Nothing alive existed yet to be burned by it, so the difference between harmful and harmless held little meaning in a world built only of stone, water, and gas. Light fell everywhere with a rawness no shaded afternoon has ever offered, meeting bare rock and open water without resistance. The sun's full force met a world with nothing yet to flinch. Impacts from space were frequent, some large enough to vaporize rock on contact and cast its remains skyward as glowing vapor. The early solar system stayed cluttered with debris, chunks of rock and ice that had never settled into a planet. And Earth's gravity kept drawing them in throughout these first ages. Most strikes were modest, leaving craters that healed into the churning crust within a few million years. But the larger ones, tens of kilometers wide, could melt or vaporize an entire region in an instant. Each such collision rewrote the local landscape, throwing molten rock into the air and letting it rain back down as fresh surface material. Where an impact this size might happen once in 100 million years today, in this era it may have happened every few thousand. The night sky glowed not with stars alone, but with streaks of falling rock, arriving so often that darkness rarely stayed uninterrupted for long. The sky was not empty, it was simply waiting to fall. A period once called the Late Heavy Bombardment may have intensified this, adding a fresh wave of impacts after things had seemingly begun to calm. Rock samples brought back from the moon, dated to between 4,100,000,000 and 3,800,000,000 years ago, showed a cluster of impact melt ages that some scientists once read as evidence of a sudden late surge in collisions. If true, this would mean the inner solar system flared back into chaos long after the worst violence of planet formation had passed. More recent analysis has cast doubt on this reading, and many researchers now suspect the pattern may reflect where samples happen to be collected, rather than a genuine spike in bombardment. The evidence remains stubbornly unclear, neither confirming nor ruling out this dramatic second act. We do not know, even now, whether Earth endured one long taper of impacts or two distinct waves separated by a lull. What is certain is that whichever shape it took, the bombardment left both worlds scarred for ages afterward. Whether that bombardment truly spiked later remains scientifically contested. Among researchers piecing together the Hadean's timeline, this argument has lasted decades without resolution. The dispute rests on fewer than a dozen lunar impact basins, whose melted rock all seems to date to a narrow span near 3.9 billion years ago. Some scientists read this clustering as proof of a genuine late surge in collisions. Others argue it may simply reflect where astronauts and probes happen to gather samples, a bias of geography rather than history. The distinction matters, because it changes how violent we imagine those final throes of planet building truly were. A courtroom might demand a verdict, but the rock record offers only probability and patience. The truth may lie buried in basins no mission has yet reached. For now, the bombardment's second act remains a story half told. Some evidence suggests asteroid impacts were simply a steady, ongoing rain. Rather than a single sharp surge, the Hadean sky may have delivered a long, unbroken drizzle of collisions, tapering slowly rather than spiking suddenly. Crater counts across several ancient lunar terrains show no obvious jump in frequency, only a gradual decline stretching across hundreds of millions of years. If this reading holds, the early solar system's chaos was not an event but a condition, a background hum of falling rock that simply grew quieter with time. This would mean Earth's surface was reshaped again and again, not by one dramatic chapter, but by ceaseless small revisions. Where popular imagination favors a single catastrophe, the evidence increasingly points toward endurance instead. A world worn down slowly rather than struck once hard. The bombardment, in this view, never truly stopped. It only faded. The sky above would have glowed with frequent incoming fireballs. On any given night in this early world, several streaks of falling rock might cross the darkness, some no larger than a house, others vast enough to outshine a moon that did not yet fully exist. Each fireball marked a piece of the solar system's leftover material, finally finding a place to land. Most burned apart in the thin, changing atmosphere, scattering fine ash across the cooling ground. A few, large enough to survive the fall, struck with enough force to shake the crust for hundreds of kilometers around. No eye watched any of it. There was no shoreline yet, no forest, no ear to hear the impact roll away into silence. The light of those fireballs traveled across an empty planet, brilliant and utterly unseen. It was a sky rehearsing for a world that had not yet learned to watch it. Solid crust likely began forming within Earth's first 200 million years. As the outer layers of the molten planet lost heat to space, a thin skin of rock could finally cool below its melting point and harden at the surface. This happened remarkably early, given how violent the surrounding bombardment still was, and it suggests that cooling and destruction proceeded side by side, rather than one waiting for the other to finish. The first crust was likely dark and dense, closer in composition to the basalt that floors our oceans today than to the pale granite of modern continents. Its formation marked the moment Earth stopped being purely a ball of molten rock and became, however briefly, a world with a surface. That surface would not last long in any single form, broken and remade constantly by heat from below and impacts from above. Still, a boundary had been drawn. The planet finally had a skin, however fragile. This crust was thin, unstable, and probably recycled quickly into the mantle. Heat from the planet's interior still pressed upward with enormous force, and any solid layer riding above it faced constant strain from below. Estimates suggest early crust may have lasted only a few million years in any one place before sinking back into the molten interior, melting again into the material it had risen from. This cycle, forming and sinking, may have repeated itself many thousands of times across the Hadean. Nothing built up the way continents do today, layer resting patiently on layer for billions of years. Instead, the surface behaved more like the skin on a pot of simmering liquid, wrinkling, breaking, and dissolving back into the depths almost as soon as it appeared. No trace of that original crust survives to be held or studied directly. What remains is only the argument for its existence, written in the chemistry of much younger rocks. Whether plate tectonics operated in the Hadean is still unresolved. Modern Earth's crust is broken into a fitted mosaic of moving plates, sliding past and against each other over millions of years. But no one knows when that system first began. Some geologists argue that something resembling plate motion could have started almost immediately, driven by the same vigorous heat flow that kept the mantle churning. Others suspect the earliest crust was too thin and too easily destroyed to organize into anything so structured, remaining instead a patchwork of drifting, half-formed fragments. Chemical clues from ancient zircon crystals, tiny and nearly indestructible, hint at conditions that could support either story equally well. The distinction shapes how we imagine the planet's early architecture, whether ordered or chaotic. For now, both possibilities sit side by side in the scientific literature, neither confirmed, neither dismissed. The ground beneath that first ocean remains, in this sense, still unmapped. Some geologists propose a cool early Earth with patches of solid crust, rather than an unbroken ocean of magma. This view imagines a surface cooling faster than expected, dotted with rafts of solid rock floating atop the still molten interior. Zircon crystals recovered from Western Australia, some dated to nearly 4,400,000,000 years ago, support this possibility since they require liquid water and a relatively stable surface to form at all. Not a molten hell, and not the calm world we know today, but something caught between the two, cooling in patches while still glowing red in others. If true, oceans may have existed far earlier than once believed, lapping quietly against small islands of solid stone. Standing on one of those rafts, the air would have scalded, the ground firm but trembling, steam rising where the water met warmth from below. The Hadean, it seems, may have worn more than one face at once. Zircon crystals from Australia hint that solid ground existed by then. In the far outback of Western Australia, a low range of hills holds fragments of the Hadean itself, pressed into sandstone far younger than the grains within it. The crystals are smaller than a grain of rice, yet each one carries a chemical memory of the rock it once crystallized from. They do not prove continents or even islands, only that somewhere on the young Earth, molten material had cooled enough to form solid mineral. This is enough to overturn the picture of an unbroken ocean of fire covering the whole planet at once. Where older models imagined only heat, these grains suggest patches of true stone, however small, however scattered. To hold one of these crystals is to hold a fragment of the planet's very first skin. It is smaller than a fingernail, and older than almost everything else on Earth. These zircons, from the Jack Hills, date to about 4,400,000,000 years old. Scientists measure their age through the slow decay of uranium locked inside each crystal, a clock that ticks at a rate no heat or pressure can alter. The number places their formation within the planet's first 200 million years, closer to Earth's birth than to any event we can picture with ease. Small margins of error remain, a few tens of millions of years in either direction, though the crystals themselves resist almost any attempt to erase their record. Every other rock from that era has long since melted, folded, or worn away, recycled by a planet that rarely keeps its own history intact. Only these tiny grains survived, passed down through billions of years of upheaval, like a message sealed inside stone. They are, in every sense, the oldest storytellers Earth has left. They are the oldest known terrestrial minerals on the planet, and nothing else found on Earth's surface comes close to their age. Meteorites can be older still, fragments of the solar system's earliest debris, but those formed elsewhere, drifting through space before falling to ground. The Jack Hill's zircons formed here, from material that was already part of this planet, which makes their survival more remarkable rather than less. No lava flow, no mountain building, no billion years of erosion managed to destroy them completely. For geologists, they function like a narrow window cut into a wall, otherwise bricked shut, offering a limited view into conditions that left almost no other trace. The view is partial and often ambiguous, yet it is the only one available. Everything we think we know about the earliest crust rests on grains this small. Oxygen isotopes within them suggest liquid water may have already existed. Isotopes are simply different versions of the same element. Atoms of oxygen that carry slightly different weights depending on how many neutrons sit inside them. The ratio between two of these forms, oxygen 18 and oxygen 16, shifts depending on whether a mineral crystallized in dry heat or in the presence of water at moderate temperatures. Within several Jack Hill's zircons, that ratio points toward crystallization in contact with water cool enough to remain liquid, not the boiling remnants of a molten surface. This does not prove an ocean, only that water, in some form, touched the rock before it hardened. The findings surprised many, since a young Earth without water had long seemed the safer assumption. If the reading holds, water was present far earlier than the models once allowed. Stone, it turns out, can remember dampness for 4 billion years. If true, oceans could have formed far earlier than once assumed, perhaps within the planet's first few 100 million years, rather than its first billion. Earlier models placed the first stable seas well after the worst of the bombardment had passed, once the surface had time to cool and settle into something closer to calm. The zircon evidence suggests a messier timeline instead, with liquid water present even while impacts and heat still shaped much of the surface elsewhere. This does not mean oceans covered the planet uniformly, only that pockets of liquid water existed somewhere at some point this early. Imagine a sea small enough to cross in a single afternoon, ringed by dark rock still warm from below, existing quietly while the rest of the world remained inhospitable. Such a place would have left almost no trace beyond the crystals that happened to form within it. The evidence is thin, yet water this old reshapes the earliest window in which life could have begun. Water likely arrived partly from the planet's own building blocks, rather than being added entirely by impacts long after Earth had formed. The dust and rubble that gathered together to build the early planet were not uniformly dry, some fragments locking small amounts of water into their mineral structure from the very start. Carbonaceous chondrites, a class of rocky meteorites still found today, contain water bound within clay-like minerals, at levels of a few percent by weight. If similar material contributed to Earth's formation, then a portion of every ocean now on the surface may trace back to ingredients present before the planet had a shape at all. This shifts the story away from a single dramatic delivery and towards something slower, built into accretion itself. Comets and water-rich asteroids likely still arrived afterward, contributing more. But the foundation may have come first. Water in this telling was never a visitor. It was there from the beginning. Hydrated minerals within accreting rocks may have released water while heating. As the pressure and temperature of a growing planet slowly broke their structure apart. Clays and other water-bearing minerals hold molecules of water within their crystal lattice, stable at the surface, but unable to survive the heat generated deep inside a forming world. As the young Earth grew heavier and hotter, these minerals began to break down, freeing their trapped water as vapor that could rise toward the surface. Over enough time and enough accumulated rock, that vapor added up to volumes capable of forming clouds, rain, and eventually pools of standing water. This was not a single event, but a gradual sweating of the interior, spread across millions of years of continuous growth. The oceans, in this light, did not arrive so much as seep outward from the planet's own body. Earth, in a sense, breathed its water into being. Comets and water-rich asteroids may have delivered additional water later. This happened after Earth had already cooled enough to hold on to what it had, during a long stretch of bombardment known as the late accretion. Some comets carry water with a slightly different ratio of hydrogen to its heavier form, deuterium, and scientists have compared these ratios to Earth's oceans to test how much comet water might have arrived. The match is imperfect, suggesting comets were a minor contributor rather than the main source. Even a small delivery, spread across millions of impacts, could have added meaningfully to the growing volume held at the surface. A single strike leaves only a trace, yet countless strikes over deep time can leave an ocean. Each fragment carried only a trace, a few molecules locked in ice and dust. Yet trace upon trace does not stay trace forever. The bombardment thinned, the water stayed. Nothing about Earth's ocean owes its existence to one source alone. The exact source of Earth's oceans remains an open scientific question. Researchers can measure the chemistry of ancient rocks and compare it to meteorites, comets, and the solar wind. Yet no single measurement settles the matter completely. The ratio of hydrogen to deuterium in ocean water points towards some mixture of homegrown minerals and later arrivals, but the exact proportions are still debated. We do not know precisely how much of the ocean formed from water already inside the planet's building blocks, and how much rained down afterward from space. What is certain is only the outcome, a world covered in liquid water within its first several 100 million years. The uncertainty does not diminish the achievement so much as widen it, since more than one path may have led to the same result. Perhaps every young planet with the right ingredients finds its way to water, whichever road it happens to take. The ocean is settled. Its origin is still being written. Once temperatures cooled enough, water vapor condensed into the first rain. Earth's surface had been too hot for liquid water to exist, holding its water instead as a dense blanket of vapor thickening the early atmosphere. As the crust solidified and heat radiated away into space, temperatures at last dropped below the boiling point of water, and the vapor above began to fall. This was not a passing shower, but a sustained downpour, falling for what may have been thousands of years without pause, as the atmosphere emptied itself onto the cooling rock below. Fossil evidence cannot capture rainfall from 4 billion years ago. So this picture comes from models of heat loss and atmospheric chemistry rather than direct observation. Picture rain falling onto ground, still warm enough to send it back up as steam in places, hissing where it landed. Little by little, the vapor thinned, and the pools below grew wider. The sky was emptying itself into the ground it had once risen from. These early oceans may have covered the entire planet in shallow water. Without mountains or continents to interrupt the surface, there was nothing to hold the water into deep basins the way ocean trenches do today. Some estimates suggest an average depth of only a few hundred meters across the whole globe, spread thin over rock that had barely finished cooling. A shallow global ocean like this would have behaved differently from today's seas, warming and cooling faster, and letting sunlight reach the bottom nearly everywhere it fell. Whether the water pooled evenly or gathered into slightly deeper basins carved by early impacts is still uncertain, since no rock from that time survives to measure it directly. A traveler crossing such a world would have seen no coastline at all, only water meeting more water at every horizon. There was no shore to stand on, and nothing yet that needed one. The planet, for a time, was simply one continuous sea. No continents rose above the waterline for a very long stretch. The crust that first solidified was dense and basaltic, similar to the rock that floors today's ocean basins, and this kind of crust sits low rather than rising into dry land. Continents require a lighter, more buoyant type of rock called granite, which forms slowly through repeated melting and separation deep within the crust. A process that may have taken several 100 million years to produce enough material to break the surface. A few small volcanic islands may have poked through the water here and there, dark and short-lived, but nothing resembling a landmass. Without continents, there was no erosion carrying minerals into the sea, no river deltas, no shoreline sediment building up in layers. The entire visible world was water meeting more water, uninterrupted by anything solid enough to last. Land, when it finally came, would change nearly everything that followed. For now, the planet had only one kind of surface to offer. The Hadean Ocean would have looked dark, steaming, and utterly still. No blue reflected from its surface, since the sky above Frin held none of the oxygen-rich clarity we know now. Only a haze of carbon dioxide and other gases that gave the whole scene a dim, reddish cast. Heat still radiating from below kept mist rising constantly off the water, so that the boundary between sea and sky would have blurred into a single grey wash. There was no wind pattern yet, capable of raising the kind of waves we associate with oceans, and there was certainly no life to stir the surface from below. Sound would have carried strangely across such a scene, an occasional distant rumble of volcanic activity, the only interruption to what was otherwise silence stretching for millions of years. To stand at the edge of this water would be to feel warmth rising through mist, with nothing moving anywhere in sight. It was an ocean holding its breath long before there was anyone to notice. Below the surface, heat from impacts and radioactivity kept water hot. Even as the surface cooled enough for oceans to form and rain to fall, the deep rock beneath those waters stayed warm, heated by two separate sources working together. Leftover heat from the planet's violent formation still radiated outward, while the slow decay of radioactive elements such as uranium, thorium, and potassium added a steady supply of new heat from within. Together, these sources kept portions of the seafloor warm enough to drive circulation, pulling cold water down through cracks in the crust and pushing heated, mineral-rich water back up through vents. This kind of system exists today at hydrothermal vents deep in modern oceans, where water emerges dark with dissolved minerals and warm enough to support entire ecosystems around it. In the Hadean, the same process ran without anything living nearby to use it. Heat rose, minerals dissolved, and water carried both back into the sea, again and again, in a cycle powered from below rather than above. The ocean's surface may have looked still, but its floor was never quiet. Hydrothermal vents on the seafloor may have formed within these young oceans. Deep beneath the still, steaming surface, the young crust was already cracked and restless, venting heat that never stopped moving upward from below. Some of these vents likely rose as mineral chimneys, not unlike structures seen at ocean ridges today, which can grow as tall as a 3-story building through centuries of gradual mineral deposit. No fossil chimney from the Hadean has ever been found, since the earliest crust was later buried, melted, or worn to nothing. So the case rests on chemistry and comparison rather than direct evidence. Still, these vents would have mattered, offering a steady source of heat and dissolved minerals in a world that otherwise had almost nothing fixed or gathered. Where the ocean above stayed dark and motionless, the vents below kept moving, building shape out of chaos. To picture one now is to see a narrow spire standing upright in blackness, its edges glowing faintly with mineral color as heated water drifts upward past it. The seafloor, it seems, was already at work long before anything alive could take notice. Such vents release mineral-rich heated water into cooler surrounding seas. The water leaving a vent opening could reach temperatures near 400 degrees Celsius, kept from boiling only by the crushing pressure of the deep ocean above it. Within a few feet of that opening, the surrounding water might sit barely above freezing, cold enough to numb, so the two extremes existed side by side without truly mixing. Carried in that heated water were dissolved metals pulled from the rock below, iron and sulfur among them, giving the plume its dark, cloudy color as it billowed upward. This sharp boundary between hot and cold, rich and empty, created conditions unlike anything found on the calm surface far above. A kettle boiling on a stove reaches its heat gently and evenly. A vent achieves something closer to force contained within stillness, heat pushed through narrow cracks in solid stone. To stand near such a place, if standing were possible, would mean feeling scalding water against numbing cold within arm's reach. Few places on the early Earth held so much difference in so small a space. Some scientists propose these vents as candidates for life's first chemistry. The idea holds that the steep differences in temperature and mineral content around a vent could have driven simple chemical reactions long before anything resembling life existed. Certain rock structures at vent sites contain tiny chambers and channels only a fraction of a millimeter wide, spaces that could have concentrated molecules and held them together rather than letting them drift apart into the wider ocean. No one claims these vents contained anything alive, only that they offered a setting where the raw ingredients might gather and interact under steady conditions. This matters because most chemical reactions need concentration and repetition to lead anywhere, and open ocean water rarely offers either. Compared to the vast, dilute expanse of the Hadean Sea, a vent's narrow channels look almost deliberate in their structure, though nothing designed them at all. To picture molecules pooling in such spaces is to picture chemistry given a quiet corner to work in, away from the churn of the larger ocean. The vents may not have made life, but they may have given its ingredients somewhere to wait. Alkaline hydrothermal vents create natural chemical gradients across thin mineral walls. Unlike the black, sulfur-rich vents that spew acidic fluid, alkaline vents release water that is warm rather than scalding and mildly basic rather than acidic, closer in feel to seawater mixed with baking soda. Between this alkaline fluid and the more acidic ocean around it sits a thin wall of mineral rock, sometimes no thicker than a sheet of paper, riddled with microscopic pores. Across that thin barrier, charged particles naturally flow from one side to the other, seeking balance the way water seeks the lowest point in a landscape. This flow of charge is not electricity in the way a battery produces it, but it shares the same basic principle, a difference in charge doing work simply by trying to even itself out. On a planet with no life yet to notice, this quiet electrical tension existed anyway, embedded in stone. It ran for as long as the vent stayed active, asking nothing and answering to no one. These gradients resemble the energy systems found in living cells today. Every living cell, including the ones inside a human body, keeps a difference in charge across its outer membrane, moving particles from one side to the other and drawing energy from the imbalance it creates. The similarity between that process and the charge gradient across a thin vent wall has led some to wonder whether life's earliest energy system was, in effect, borrowed from geology before biology existed to claim it. Imagine a barrier not much different from the vent's mineral wall, only thinner, softer, alive, still using the same basic trick of separating charge to do useful work. If the comparison holds, then one of life's most fundamental habits, older than breathing, older than eating, may reach back to stone and mineral, rather than to anything resembling flesh. This does not mean the vent was alive in any sense, only that it may have modeled a pattern life would later adopt and refine. The trick came first. The living things that used it came later, borrowing what the rock had already worked out. Amino acids, life's building blocks, could have formed through simple reactions. These molecules, strings of carbon, hydrogen, oxygen, and nitrogen arranged in specific patterns, serve today as the components proteins are built from, present in every living cell on Earth. Laboratory work has shown that combinations of water, simple gases, and a source of energy can produce several kinds of amino acids without any living process involved at all, given the right conditions and enough time. Vent environments, with their steady heat and mineral surfaces to concentrate molecules, offer one plausible setting where such reactions might have played out again and again across millions of years. No single amino acid found this way proves that life began at a vent, since forming a building block is a very different thing from assembling it into something that can grow and copy itself. Even so, the fact that these molecules can appear from non-living chemistry at all softens the line between rock and organism. Something that would one day help build a body first appeared, quietly, in water and stone. Laboratory experiments show lightning and volcanic gases can produce such molecules. In the 1950s, a well-known experiment combined water, methane, ammonia, and hydrogen inside a sealed glass system, then ran an electrical spark through the mixture to stand in for lightning striking early Earth's atmosphere. Within a week, the water inside had turned a deep reddish brown. An analysis found several amino acids had formed among the murky residue, produced entirely from simple gases and electricity. This did not recreate life, and later research questioned how closely the original mixture matched the Hadean's actual atmosphere, but the basic result has held up in various forms since. Volcanic eruptions, common across the young Earth, released many of the same gases used in that glass system, and lightning during ash-heavy storms could have supplied the spark. Between vents below the ocean and lightning above it, early Earth offered more than one route toward the same simple molecules. The ingredients, it turns out, were never especially hard to make. What came next is a longer, quieter story, still being read from rock. Meteorites may have also delivered organic molecules formed in space. Long before Earth had oceans or continents, the cloud of dust and rubble that built the solar system was already rich in carbon chemistry, cooked slowly in the cold between forming worlds. Fragments of that early material kept falling for hundreds of millions of years, some no larger than sand grains, others the size of houses, each one a small parcel of ancient chemistry striking a young and mostly empty planet. Not every arrival mattered, and most burned away or shattered on impact without leaving anything behind. Still, across enough time, enough of that material likely survived the fall to matter, adding to whatever was already forming in Earth's own water and rock. Picture a sky doing double duty, delivering both violence and ingredients in the same long rain of stone. Earth, it seems, did not have to make everything it needed by itself. Carbon-rich meteorites called carbonaceous chondrites contain amino acids and sugars. These are among the oldest, least altered fragments left from the solar system's formation, dark and crumbling, holding chemistry that has barely changed since before any planet existed. Modern examples of this type have been found to carry more than 70 different amino acids, several of which also appear in living cells today, alongside simple sugars related to the ones used in RNA. None of this proves such meteorites seeded early Earth directly, since laboratory chemistry can sometimes mimic space chemistry by coincidence. Even so, their sheer abundance of biological-looking molecules is difficult to dismiss as unrelated. It is as though the raw material for a chemistry set had been drifting through space long before there was anywhere to use it. A dark rock falling through a young sky could have carried more promise than weight. Comet ice, too, carries traces of complex carbon-based chemistry. Comets are loose bundles of ice, dust, and frozen gas, formed in the coldest outer regions of the solar system, and occasionally sent inward on long, looping paths toward the sun. Spacecraft that have sampled comet material directly have found simple organic compounds locked inside the ice, including molecules that can serve as starting points for amino acids, once warmed and given the right chemistry. We do not know how many comets struck the young Earth, since ice leaves little behind once it melts and boils away. What can be said is that comets, like meteorites, were part of the same broad delivery system, one more route by which space chemistry reached a planet still assembling itself. Imagine countless small envelopes of frozen chemistry, arriving quietly, then simply vanishing into the water. Nothing about their arrival needed to be dramatic to matter. Whether life's ingredients came from Earth or space remains debated. Two broad pictures exist side by side, neither one able to fully rule out the other with the evidence currently available. In one, Earth's own chemistry, driven by lightning, heat, and vent minerals, produced everything needed without outside help. In the other, meteorites and comets supplied a meaningful share of the necessary molecules, arriving ready-made from space. Fossils can only tell us so much about a period that left no fossils at all, and the earliest rocks that might have recorded an answer were destroyed long ago by the planet's own restless surface. Most researchers now suspect both processes played some part, working together rather than in competition. The next time you look up at a clear night sky, remember that some of what fell from it may once have helped build something living. The answer, for now, rests quietly between the ground and the stars. Clay minerals may have acted as surfaces where molecules could concentrate. Clay forms when certain rocks weather slowly in water, breaking down into thin, stacked sheets of mineral only a few atoms thick, each sheet carrying a faint electrical charge along its surface. That charge can attract and hold on to organic molecules drifting nearby, gathering them out of open water and pressing them close together in tiny, crowded spaces between the layers. In an ocean where useful molecules were otherwise scattered thin and rare, this kind of gathering may have mattered more than any single reaction. Clay does not create life, and holding molecules together is not the same as organizing them into something functional. Still, concentration is often the first quiet step before anything more complicated can occur. A fine, ordinary sediment may have done some of life's earliest, least celebrated work. Such surfaces might have helped simple chemicals link into longer chains. On their own, dissolved in open water, small molecules drift apart faster than they combine, and any chain that begins to form is easily broken before it grows very far. Clay's narrow spaces change that balance, holding molecules near one another, long enough for chemical bonds to form between them, sometimes stringing short chains into longer ones under laboratory conditions meant to mimic those early surfaces. Longer chains matter because size and structure are what eventually allow a molecule to do more than simply exist, to fold, to bend, to interact with its surroundings in specific ways. This does not explain how such a process began outside a laboratory, and the record of it, if it happened, has long since crumbled to nothing. It offers, instead, a plausible bridge between simple chemistry and something more elaborate. Somewhere between grains of clay, complexity may have first found room to stretch. RNA molecules, capable of storing information, may have formed this way. RNA is built from a backbone of sugar and phosphate linked to 4 kinds of chemical letters arranged along its length, an arrangement that can both hold a pattern and, under certain conditions, copy it. Some scientists propose that clay surfaces, or similar mineral templates, helped early RNA-like chains assemble from smaller pieces, one link joining the next in a slow, repeated process across long stretches of time. No one has recreated this fully from start to finish, and each proposed step still carries open questions that current chemistry cannot fully resolve. What makes RNA compelling is that a molecule holding information is a very different thing from one that merely reacts, since information can be kept and copied and changed. Where ordinary chemistry repeats itself, information-bearing chemistry can begin to drift and vary. A pattern, once it could be copied, no longer needed to be remade from nothing each time. The idea that RNA came before proteins is called the RNA world hypothesis. It sits at the center of most thinking about how the Hadean's chemistry might have crossed into something we would call living. The hypothesis holds that RNA once served 2 roles, now split between separate molecules, carrying genetic information, the way DNA does today, while also acting the way proteins do now, folding into shapes that speed up chemical reactions. No one claims this happened in a single leap, and many steps in the proposed sequence remain untested outside a laboratory. If true, it would mean life did not need 2 complicated inventions at once, only one molecule doing double duty until simpler solutions came along. Modern cells split these jobs between specialists. An RNA world would have made do with a single generalist, clumsy but sufficient. Picture one molecule, patient and unglamorous, quietly holding open a door that biology would later widen. It was not elegant, it only had to work. A membrane enclosing such molecules could have formed the first protocell. This is the step where chemistry begins to resemble biology, however faintly, wrapping loose reactions inside a boundary that separates inside from outside. Laboratory versions of these structures are called protocells, simple sacs a few thousandths of a millimeter wide, and they can trap RNA-like molecules within a wall, without any of the machinery real cells use today. They are not alive by any working definition, since they cannot reliably copy themselves or repair damage. Still, a boundary changes everything a boundary touches, keeping useful molecules close together instead of drifting apart into open water. Where the ocean offers endless dilution, a membrane offers a room, small and enclosed and cooperative. Imagine a droplet no wider than a whisper, holding its contents together against a whole ocean trying to pull them apart. A wall, however thin, was the beginning. Fatty molecules naturally curl into tiny spheres resembling simple cell walls. This tendency requires no plan and no life, only the ordinary physics of molecules that dislike water on one end and tolerate it on the other. Such molecules are called lipids, and when mixed into water, they spontaneously arrange themselves into hollow spheres called vesicles, hiding their water-repelling ends inside a double layer and letting the water-tolerant ends face outward and inward at once. This happens today in any kitchen sink, wherever soap meets water, and it likely happened just as readily in the Hadean's ponds and pools. The consequence is that a container for life's chemistry may have assembled itself for free, using nothing but ordinary molecular preference. Nothing designed it. It simply could not arrange itself any other way. Picture countless small spheres, forming and dissolving endlessly along a shoreline, waiting for nothing in particular to happen inside them. Most held nothing worth keeping. A few perhaps did. No fossil evidence survives from this hypothetical earliest chemistry. Every idea about RNA, membranes, and protocells belongs to a stage of Earth's history that left no rock, no mineral trace, and no chemical signature we can point to directly. The oldest confirmed fossils appear roughly 3.5 billion years after the Hadean's midpoint, already showing organisms complex enough to leave a visible imprint. Between that point and the era we are describing lies a gap of hundreds of millions of years, entirely unwitnessed by any surviving record. This absence does not disprove any of the ideas, but it does mean they remain proposals rather than histories, built from chemistry rather than from stone. Where later epochs left shells and footprints, this one left nothing anyone has found. Consider that we are reconstructing a beginning from silence, the way one might guess at a room's furniture, from the dust that settled after it burned. The chemistry may be true. The evidence, if it ever existed, is gone. Everything about life's origin in the Hadean remains inference, not proof. Scientists build these accounts the way a person might rebuild an unwritten conversation from a few surviving words, working outward from chemistry that is known toward events that can only be guessed. Laboratories have shown that amino acids, simple sugars, and RNA-like fragments can form under conditions resembling early Earth, tested across decades of controlled experiments meant to imitate a planet no one witnessed. None of this shows that life definitely arose this way, only that it plausibly could have. The distinction matters, since plausibility is not the same as history, and a working recipe is not the same as a memory. Where a courtroom needs proof, this science works instead with careful, patient likelihood. Consider each proposed step as a lantern held up in a dark hallway, illuminating one plausible path among many that might have led to the same door. The hallway is long. The lanterns do not reach its end. Some researchers argue life could not have survived the era's violence. The Hadean was scarred by impacts large enough to boil oceans and strip away atmospheres, events severe enough that some scientists doubt any early chemistry could have endured them. One especially large collision, the same event thought to have formed the moon, would have briefly turned much of Earth's surface molten. erasing anything fragile that came before it. This argument does not deny that early chemistry existed, only that it may have been destroyed and restarted many times before anything durable emerged. If correct, life's true beginning might sit closer to the Hadean's final centuries than to its first, where a steady world allows slow experimentation. A battered one keeps resetting the clock before any experiment finishes. Picture a fire lit and extinguished 100 times before it finally caught and held. Violence in this telling was not life's enemy. It was simply its slow, repeated interruption. Others argue sheltered pockets, deep underwater, may have stayed calm enough. Beneath the surface chaos, the deep ocean floor offered a kind of shelter that the open air and shallow water could not, insulated by hundreds or thousands of meters of water above. Hydrothermal vents, cracks in the seafloor releasing heated, mineral-rich fluid, are proposed as one such refuge, largely unaffected by impacts and storms happening far above. No vent from the Hadean survives to be examined directly, so this idea rests on younger vents used as modern analogues, not as direct witnesses. If pockets like these existed, they would have offered steady warmth, steady chemistry, and long stretches of undisturbed time, exactly what fragile new molecules would have needed. Where the surface changed by the hour, the deep sea floor may have changed hardly at all. Imagine warmth rising quietly through darkness, untouched by whatever was happening far above it. Calm, it seems, did not vanish from the Hadean. It simply moved out of sight. Phosphate, essential to DNA and RNA, was likely scarce on early Earth. Among the elements needed to build life's molecules, phosphorus proved the hardest to come by on the young planet. Phosphate forms the backbone of both DNA and RNA. Yet on the Hadean's surface, it existed mostly inside minerals that dissolve slowly in water, if at all. This does not mean phosphorus was rare in the crust, only that it rarely appeared in a form early chemistry could actually use. Without accessible phosphate, the molecule that would eventually carry genetic instructions had no easy way to assemble its backbone. Carbon and nitrogen arrived steadily from the atmosphere and from falling debris, but phosphorus stayed locked away, reluctant to join the mixture. A kitchen stocked with almost every ingredient except the one the recipe needs most gives some sense of the trouble. Life, it seems, was still waiting on a single missing shelf. Certain minerals, like schreibersite from meteorites, may have supplied it. If phosphorus could not be found on the ground, perhaps it fell from above. Schreibersite, an iron-nickel phosphide found in meteorites, arrived on Earth in meaningful quantities during the heavy bombardment of the late Hadean, carried inside rocky and metallic fragments from space. Not every meteorite carried it, and much of what landed reacted with water at different speeds, some almost instantly. When schreibersite dissolves, it releases phosphite, a soluble form of phosphorus that early chemical reactions could use far more readily than anything locked in surface rock. Modern weathering releases phosphate slowly, over millions of years, grinding stone into soil, while a single meteorite strike could deliver it almost at once. To picture a small stone falling into shallow water is to picture an unlikely delivery arriving from beyond the sky. Sometimes what a young planet lacked, the sky simply provided. Hydrogen cyanide, a simple molecule, may have driven early prebiotic chemistry. In the thin, changing atmosphere of the young Earth, lightning and ultraviolet light constantly broke gases apart and pushed their pieces back together in new arrangements. Hydrogen cyanide, built from just 3 atoms, forms readily when nitrogen and carbon compounds are struck by energy, and experiments recreating Hadean conditions produce it with ease. On its own, the molecule is simple and lifeless, no more remarkable than any other small compound drifting through the air. Yet hydrogen cyanide links together into longer chains, and those chains fold into the precursors of amino acids and nucleic acids, the raw pieces from which proteins and genes are eventually built. A modern laboratory assembling such molecules relies on careful instruments and controlled conditions. The early Earth had only sunlight, standing water, and an uncounted stretch of time. Standing beneath that sky, you would have seen only ordinary rain, never guessing it carried the earliest pieces of something that would one day think. A small molecule, patiently rearranged, can become the seed of everything. Under ultraviolet light, cyanide-based compounds can form sugars and nucleotides. Without an ozone layer to filter it, the Hadean sky let ultraviolet radiation strike the surface at levels far beyond anything living things endure today. Laboratory work recreating those conditions shows that solutions of hydrogen cyanide, exposed to ultraviolet wavelengths, can generate ribose and related sugars alongside the nucleotide bases that spell out genetic code. These experiments do not prove such reactions occurred on the real Hadean Earth, only that the chemistry works under conditions thought to resemble it. If the reactions did occur, ultraviolet light would have acted less as a danger and more as an engine, driving transformations that gentler sunlight alone could not manage. Such radiation now damages living cells. Yet on a world with no cells left to damage, it may instead have helped assemble the materials cells would later be built from. There is a quiet strangeness in picturing harsh light as a builder rather than a hazard. What harms life now may once have helped assemble it. Molecular clock estimates place life's true origin near the Hadean's end. Rather than reading rock layers, this method reads the small differences accumulated between the genes of living things today and works backward from there. By comparing mutation rates across many species, researchers have estimated that the last common ancestor of all known life diverged somewhere between 4.1 and 3.9 billion years ago. The method carries real uncertainty since mutation rates have not stayed constant across billions of years, and no organism from that time survives to be measured directly. Even so, it offers a check on the fossil and chemical evidence that does not depend on any rock having survived at all. Fossils require stone that endured the ages intact, but a molecular clock only requires living descendants, tracing change backward through generations that are still here. A living cell examined under a microscope today carries, without knowing it, a kind of record still running from that first divergence. The past, it seems, is written into the present as much as into the rock. This would place life's beginning around 4 billion years ago. Set against the timeline of the Hadean, that date falls only a few 100 million years after Earth had cooled enough to hold liquid water at all. 4 billion years ago, the moon still hung closer in the sky. Days lasted only a few hours longer than an afternoon nap. And impacts still fell with some regularity across the crust. This figure is an estimate drawn from converging methods, not a fixed date recorded anywhere, and it could shift as new evidence arrives. If it holds, life did not wait for calm to fully settle before it began experimenting with chemistry of its own. A modern mind imagines biology needing gentle, stable conditions to begin. Yet this estimate suggests the earliest chemistry got underway while the world was still finding its footing. It is worth sitting with the thought that something alive may have existed, while the sky above it still occasionally lit up with falling stone. The world did not wait to be finished before life began writing itself into it. If accurate, life arose remarkably soon after Earth became habitable at all. Habitability itself is a narrow target, requiring liquid water, moderate temperatures, and a surface no longer regularly sterilized by impact. Estimates suggest Earth crossed that threshold sometime around 4.2 to 4.4 billion years ago, leaving only a few 100 million years, perhaps less, before the molecular clock's estimated origin of life. A few 100 million years sounds vast, but on the scale of planetary history, it is a narrow window, barely more than a tenth of Earth's total age. Such a short gap suggests that whatever conditions life requires to begin may not be as difficult to reach as scientists once assumed. Where many expected a long, uncertain struggle before life managed to take hold, the timeline instead suggests something closer to readiness. Standing at the edge of that narrow window, you might sense chemistry itself leaning toward life from the very beginning, eager rather than reluctant. Life, it turns out, may not have been a rare accident. It may have been closer to inevitable. No rock from Earth's earliest 100 million years has ever been found. This is the plainest fact of the Hadean, the one that shapes every other claim about it. The earliest crust that formed after the planet cooled has simply vanished, melted and remade so many times that nothing original remains. This does not mean that crust never existed, only that it was recycled before anyone existed to study it. Because of this gap, scientists must infer the earliest world from what came after it, reading backward from later evidence rather than forward from direct samples. Where a geologist studying almost any other era can hold the actual stone in hand, a geologist studying this period works entirely from shadows and residue. To study the Hadean is to accept that its opening chapter has no surviving page, only the faint impression it left on everything written afterward. The earliest Earth left no diary. It left only echoes. The record of the Hadean survives only in scattered, indirect traces. Across the whole 400 million year span, evidence appears not as a continuous story, but as isolated fragments separated by long silences. A handful of mineral grains, a few chemical ratios locked in later rock, and one exceptional crystal are nearly all that remain. These traces do not connect smoothly into a timeline, and scientists openly admit that much of what happened between them is inferred rather than observed. Still, even fragments carry weight when nothing else survives, and each one narrows the range of what could plausibly have been true. Where later eras can be read almost page by page, the Hadean must be read letter by letter, with most of the text missing. To reconstruct this world is to work like someone piecing together a story from a few surviving words, trusting the gaps as much as the words themselves. The silence between traces is not empty. It is simply unread. Most of what we know comes from zircon crystals, not whole rocks. These crystals are the true archive of the Hadean, tiny and nearly indestructible, where everything around them has long since been destroyed. Zircon forms within cooling magma and locks tiny amounts of uranium into its structure, allowing scientists to date it with unusual precision. Unlike the rock that once held them, these crystals resist melting, weathering, and the slow churn of tectonic recycling, so they can outlast the very stone they formed within. Because of this durability, they can drift free of their original rock and settle into much younger sediment, carrying an ancient date inside a modern setting. Where a whole rock might vanish entirely, a single zircon grain can survive the destruction of everything around it. To hold one of these crystals is to hold a fragment of the earliest crust, smaller than a grain of sand and older than every mountain range on Earth. The record survived not in stone, but in something almost too small to see. Later tectonic activity destroyed almost every trace of the earliest crust. Earth's surface has never been still, and that restlessness is precisely why so little of its first crust remains today. Plates collided, folded, and sank back into the mantle again and again, melting older material into new rock over and over across billions of years. This process, called subduction, does not preserve what it consumes. It transforms it, erasing the original record even as it builds something new from its remains. Because of this constant turnover, almost nothing on Earth's surface today is truly ancient. In an unbroken sense, only remade from ancient material many times over. Where a fossil in soft sediment might occasionally survive intact, a rock caught in this cycle rarely does. To stand on almost any surface today is to stand on material that has been melted and reborn more times than can be counted. The earliest crust was not lost all at once. It was slowly recycled out of existence. The oldest known whole rock formation is Canada's Acasta gneiss. Exposed along the shores of a remote lake in the Northwest Territories, it is the closest thing Earth offers to an intact fragment of its ancient self. The rock is a gneiss, a type of stone reshaped by intense heat and pressure, its original minerals stretched and folded into pale, banded streaks. Unlike the zircon crystals scattered through younger sediment, this is an entire formation that survived largely in place, spared by unusual geological luck rather than pure chance alone. Its survival mattered because it gave scientists something rare, a whole structure to study rather than a single microscopic grain. Where most ancient material exists only in fragments, this formation offers something closer to a full sentence rather than a scattered handful of letters. To walk across this rock is to walk across the oldest known ground, still standing in its original place. Nothing else on Earth's surface can make quite the same claim. It dates to about 4 billion and 3 million years ago. This measurement comes from the same slow atomic decay used to date zircon, applied here directly to the whole rock, rather than a single embedded crystal. The number places its formation well within the Hadean, after Earth had cooled, but long before the world resembled anything familiar. Because the rock has been folded and reheated since then, scientists describe this date carefully, as the age of its oldest surviving mineral components, rather than a single clean moment of creation. Even with that caveat, the figure holds remarkably steady across repeated testing, lending it unusual confidence for something so old. Where younger rocks can sometimes be dated with near certainty, a number reaching this far back always carries a small, honest margin of uncertainty. To read this date is to glimpse a moment when Earth's crust was still new by any planetary measure, only a few 100 million years old. The number is not exact. It is simply the closest we have come. Even this rock, formed after the Hadean's true beginning. The Acasta gneiss, for all its age, still represents a moment nearer the eon's end than its start. Earth had already existed for roughly 200 million years before this rock took shape, time in which oceans, an early atmosphere, and perhaps even the first chemistry of life had already begun. This means the very earliest chapters of the Hadean, the ones scientists most wish to read, remain entirely unrepresented by any surviving stone. Everything from Earth's formation to this rock's creation must be reconstructed indirectly, drawn from theory, chemistry, and the scattered zircon grains that predate it. Where later history can point to a stone and say, here, this happened, the Hadean's opening act can only be inferred from what came just after it. To study this rock is to stand near the end of a story whose beginning was never written down at all. The oldest known page was never the first one. Scientists also study the moon, since its surface preserved ancient impacts. Earth's own crust erased almost everything from its earliest hundreds of millions of years. So researchers looking for that missing history often turn their attention outward instead. The moon's surface holds craters by the thousands, some dating back more than 4 billion years, untouched since the moment they formed. It has no oceans, no wind, and no shifting plates to smooth its wounds away. So what struck it once still lies written exactly as it fell. This makes the moon something like a fossil record of the space between worlds, holding evidence that Earth's own restless surface could never keep for itself. Its neighbor simply let every bruise remain exactly where it landed. To look up at the full moon is to look at a face still marked by wounds Earth once shared, long before either world settled into the shape it holds now. Its scars are also, in a way, ours. Lunar rocks returned by astronauts recorded bombardment history. Earth itself lost. Between 1969 and 1972, 6 Apollo missions carried samples home, together weighing about 380 kilograms, gathered from plains, craters, and ancient highlands. Many of these rocks, melted and reformed by ancient impacts, preserve tiny crystals whose radioactive clocks reset at the moment of each strike. Dating them revealed something unexpected. A cluster of ages crowding around 3.9 billion years, as though the moon endured a sudden storm of collisions rather than a slow scattering of them. Some scientists take this as evidence of a late heavy bombardment, a surge that may have struck Earth just as hard, though our planet kept none of the bruises. A handful of pale stones in laboratory drawers now carry a memory Earth's own crust could not hold on to. The clock stopped ticking there and never started again. Each crater on the moon likely has a twin scar somewhere on Earth. Both worlds drifted through the same swarm of rubble left over from the solar system's formation, exposed to identical hazards for hundreds of millions of years. Earth's stronger gravity would have pulled in even more of that debris than the moon ever received. Perhaps twice as much, simply because of its greater mass and pull. These impacts were not matched strike for strike, but the two worlds absorbed the same falling sky at roughly the same time. Every basin visible through a telescope tonight implies a companion wound, once opened somewhere on our own surface, larger, deeper, and long since vanished. Earth's version of that same bombardment was overwritten again and again by everything that came after it. A crater on the moon is a kind of orphaned record, missing its sibling on Earth. The evidence survived on one world and not the other. Earth's twin scars were erased by weather, water, and shifting plates. Rain fell on the fresh basins almost as soon as they cooled, carrying sediment down into their bowls and softening every sharp edge within a few thousand years. Ocean floor recycles itself back into the mantle roughly every 200 million years, dragging whole stretches of ancient crust downward and out of reach forever. A few scars might still lie folded somewhere deep within old continental cores, though none has yet been confirmed with certainty. The same restlessness that destroyed this record is also the reason Earth still has weather, oceans, and shifting ground today. The moon's stillness preserved its wounds, simply because nothing on its surface was ever alive enough to move again. Rain found those first impact basins within a geological instant, smoothing what fire had only just torn open. Healing here looked exactly like forgetting. The Hadean officially ends at 4 billion and 3 million years ago. Geologists needed a boundary to mark where Earth's mute, rock-poor beginning gave way to an eon with a lasting stone record, and this is the line they chose. The number 4 billion and 3 million was picked for a specific reason, tied closely to a single surviving rock formation rather than any planetary event. nothing actually happened on that date. No eruption, storm, or impact drew a line across the planet's surface at that precise moment. The boundary exists only in the language scientists use to organize an otherwise seamless 400 million years of change. Compared to boundaries drawn by sudden extinctions or violent impacts elsewhere in Earth's history, this one is quiet, almost administrative, chosen for convenience rather than drama. A single line on a modern chart now divides two ages that on the actual planet never noticed any difference at all. The line belongs to us, not to the rock. This boundary matches the age of the oldest known Earth rock. The date was not chosen by coincidence. Scientists set the Hadean's end to align with the age of the Acasta gneiss, since no direct evidence has ever been found from any moment after it. That grey outcrop in Canada's Northwest Territories effectively became the anchor point for the entire geologic timescale that follows. A single stone deciding where one age ends and another begins. This is not how most boundaries are drawn. Elsewhere, scientists rely on global markers, layers of ash, or sudden shifts in ocean chemistry visible on every continent at once. Here, one surviving fragment of crust was enough to set the standard for the whole planet. Visiting that outcrop today means standing at the literal starting point of Earth's readable stone record, with everything before it existing only in theory and calculation. The rock did not just survive the Hadean, it ended it. The shift into the following eon, the Archean, was gradual, not sudden. No single sunrise separated one age from the next. Impacts slowed gradually, crust thickened gradually, and the oceans, wherever they existed, simply persisted a little longer with each passing million years. This transition likely unfolded across tens of millions of years surrounding the 4 billion year mark. Too slow for any single witness, had one existed, to notice at all. It was not a catastrophe, not a single sharp boundary written in ash or fire, but a long, quiet accumulation of smaller changes settling into something more permanent. This slow shift allowed crust to thicken enough to persist for the first time, setting the stage for the first true continents still to come. Later boundaries in Earth's history would be marked by sudden extinctions visible in a single layer of rock. This one left no such line to point to. Standing on Earth's surface as the Hadean ended would have felt like an ordinary day, indistinguishable from the one before or the one after. Endings on this planet rarely announced themselves. Bombardment slowed as the solar system's debris thinned over time. The early solar system had been full of leftover rock and ice, fragments still drifting from its formation, and Earth swept many of them from its path with every orbit it completed. By around 4 billion years ago, the rate of large impacts had fallen by a wide margin, though no precise count of strikes survives anywhere in the rock record. This did not mean the sky went empty. Smaller strikes likely continued for hundreds of millions of years more, fading rather than ending outright. Each quieter century gave the crust longer to cool and harden before the next disruption arrived to disturb it. Where once a surface might be reset within a human lifetime, it could now persist for ages at a stretch, undisturbed. Picture a sky that still held streaks of light now and then, but no longer the constant fire of the ages before it. The bombardment did not stop. It simply grew tired. Earth's crust grew thicker, colder, and increasingly stable through this shift. Beneath the calming sky, the planet's outer shell was responding to the same quiet that had settled overhead. Estimates suggest the crust may have thickened from only a few kilometers to tens of kilometers across this span, though the numbers remain approximate. This was not a single hardening, but countless small additions, layer upon layer of cooled rock accumulating faster than impacts could melt it away again. A thicker crust meant less heat escaping directly from the mantle below, which in turn allowed the surface to cool further still. Modern crust, by comparison, is the distant descendant of this long thickening, stacked and folded many times since those first layers formed. To stand on Hadean ground near its end would be to feel something closer to solid footing, still warm, but no longer trembling with every passing age. Stability, once rare, was becoming the ordinary condition of the world. Oceans deepened and likely became more chemically similar to today's seas. As impacts eased and the crust held steady, water that had gathered in early basins finally had time to settle rather than boil away again. Chemical models suggest these seas were already salty, rich in minerals carried down from rock and ash, though their exact composition cannot be measured directly from any surviving sample. They were not yet identical to modern oceans, missing the long balance that living things and weathering would later provide across billions of years. Still, their basic character, a body of salt water resting on stone, had likely arrived by now. Where the earliest seas may have been shallow, restless, and prone to sudden evaporation, these later ones could hold their shape for millions of years without much disturbance. A dark, salt-heavy sea, warm at its surface and unlit in its depths, patient in a way no ocean before it had managed to be. The waters had found, at last, a kind of permanence. Whatever early life existed slowly diversified into the Archean's simple microbes. If life had already taken hold in the Hadean's final stretches, it would have been simple beyond imagining. Single cells without nucleus or memory, drifting quietly in warm water. By the start of the Archean, chemical traces in old rock suggest communities of such cells living in shallow pools and along mineral vents on the seafloor. These were not species in any sense we would recognize, but lineages of chemistry repeating itself with small variations from one generation to the next. Diversification here meant only the slow accumulation of difference, one cell's descendants drifting slightly apart from another's over countless generations, where complexity in later life would mean organs, limbs, and thought. Complexity here meant nothing more than a new way of using a chemical gradient. A single pool might have held several such lineages, each unaware of the other, none aware of anything at all. Life had not yet learned to notice itself. The atmosphere began its long, slow transformation toward what came later. Volcanic gases had shaped the Hadean sky for hundreds of millions of years, thick with carbon dioxide, nitrogen, and traces of sulfur compounds drifting close to the ground. By the eon's end, this mixture had begun shifting in proportion, though free oxygen remained absent and would stay that way for well over 1 billion more years. The change was driven less by life, which was still too sparse to matter much, and more by the slowing rate at which volcanoes and impacts fed new gas into the sky. A calmer crust released gas more slowly, and the sky above it grew correspondingly quieter in its own composition. This was not yet an atmosphere any creature could breathe, but it was inching, gas by gas, toward one that eventually could. The air over the last Hadean sunsets would have smelled faintly of sulfur and ash, heavy and still against the skin. Change, in the sky as on the ground, was arriving one small exchange at a time. Carbon dioxide levels stayed high, keeping the planet warm despite the faint sun. The young sun burned dimmer than it does now, delivering perhaps 70% of today's light and heat down onto Earth's surface. Under a fainter star, the planet should have frozen. Yet carbon dioxide had accumulated in the atmosphere at levels many times higher than the present day, trapping heat close to the ground. This greenhouse effect, though no one yet had the word for it, kept oceans liquid rather than locked away in ice. Without it, the faint young sun might have left Earth a frozen sphere, its waters solid and its chemistry stalled indefinitely. Instead, warmth persisted through gas alone, a balance struck between a weak star and a heavy, close sky. A traveller standing on the shore at this time might have felt air warmer than the sun above seemed to justify, thick and close against the skin. The planet was warm because it refused to let its heat go, not because the sun demanded it. No evidence of continents resembling today's land masses exists from this time. The end of the Hadean left no shorelines shaped like the coasts we know, no mountain ranges arranged as they are now, and no oceans bounded by familiar edges. What crust existed likely formed scattered islands and plateaus, small and volcanic, rising only slightly above restless water on every side. These fragments were not stable enough to be called continents in any modern sense, lacking the deep, buoyant roots that let today's land masses persist for billions of years. True continental crust, thick and light enough to resist sinking back into the mantle, would take much longer still to accumulate. A map drawn at this moment would show no familiar outlines, only drifting patches of stone scattered across an endless expanse of water. Such a world would look less like a planet and more like a single vast sea with a scattering of stepping stones across it. The continents were not missing by accident. They simply had not yet been made. Everything solid we now stand on came later, built from Hadean material. No mountain, no seabed, no grain of sand from that first eon has survived intact into the present. Yet the atoms that make up granite peaks and ocean floors trace back to the same molten stock that churned across the Hadean surface. Nothing was created new in the eons that followed. Matter was only rearranged, cooled, folded, and rebuilt into forms the early Earth never held. This meant the planet's first age was not erased so much as recycled, its substance carried forward into every later chapter. Where a modern quarry might feel ancient, it is young compared to the source material buried within its stone. To hold a piece of granite is to hold something shaped long after the Hadean, yet made from nothing else. The world we walk on is inherited, not original. The heat, water, and elements of that first eon never truly left. Across billions of years, Earth has cooled at its surface while carrying forward the deep inheritance of its molten start. Radioactive decay within the mantle, the same process that once helped keep the young Earth soft, still generates heat today, faint but constant. This is not the same fire that glowed at the surface long ago, but it descends from it, a quieter continuation rather than a separate beginning. Water that arrived or formed in the Hadean still moves through clouds, rivers, and oceans, cycling endlessly rather than disappearing. Where a fire in a hearth burns out and leaves only ash, this planet's inner warmth has simply dimmed without extinguishing. To stand near a hot spring today is to feel a faint echo of the world's first furnace, still breathing beneath the ground. Nothing was lost. It was only quieted. Every atom in today's oceans and rocks passed through that molten beginning. Nothing on Earth's surface arrived from some later, cleaner source. It all traces back to the same churning, overheated mass that once made up the planet. Iron in a drop of blood, oxygen in a breath of air, and silicon in a window pane all share ancestry in that early molten world, redistributed across billions of years into new forms. This is not metaphor, but chemistry. the literal continuity of matter through unimaginable transformation. Where a river might seem to end at the sea, its water was never new, only returned once more to a larger cycle. It is as though the whole planet is a single body, still carrying its earlier self forward, unnoticed, inside every smaller thing it later became. To look at a stone in your hand is to hold something older than any word for old. The beginning is still here, disguised as the ordinary. The Hadean remains largely a story pieced together from tiny clues. No written record, no fossil trace, no undisturbed rock layer survives from this eon in the way later ages left behind. Scientists rely instead on fragments, isotope ratios, trace minerals, and computer models built from the physics of planet formation, each offering a narrow, imperfect window. This is not failure, but necessity, the natural result of a world that destroyed nearly all evidence of its own beginning through heat and violence. What we know of the Hadean is therefore provisional, built more from inference than direct observation. Where later chapters of Earth's history read like a book with torn pages, this one is closer to a handful of scattered letters, some legible, most lost. To study the Hadean is to accept incompleteness as the price of reaching so far back. The story survives only in pieces, and the pieces are enough to begin. A handful of zircon grains hold nearly all we know for certain. Among Earth's oldest surviving materials, these small mineral crystals formed within Hadean magma and proved tough enough to survive every upheaval since. Found mostly in the Jack Hills of Western Australia, these zircons carry isotopic signatures, allowing scientists to date them to nearly 4.4 billion years, some of the oldest solid material ever identified. They are not the crust itself, since that crust is long gone, but tiny witnesses trapped within later rock, carried forward like sealed messages. Their chemistry hints at surface water, at temperatures cooler than pure molten rock, at a planet already more complex than a glowing ball of fire, where entire mountain ranges have vanished without trace. These grains, smaller than sand, endured everything. To examine one under a microscope is to look directly into conditions predating almost everything else we can touch. The smallest fragments carried the oldest truths. Much of this eon will likely remain forever partly unknowable. No new evidence will restore what heat, pressure, and time destroyed so completely across those first hundreds of millions of years. Scientists can refine models, discover new zircon grains, or improve isotope techniques. Yet certain details, like the exact timing of the first ocean or the specific chemistry of the first crust, may simply be lost. This is not a failure of science, but a limit imposed by the planet's own violent youth, which erased its own record before anything could preserve it. The Hadean will always be reconstructed rather than directly observed, more inference than certainty. Where later ages left books, this one left only a few water-stained pages, and some pages are simply gone. To accept this is to accept that some questions about our origins have no final answer. Mystery here is not a gap to fill, but a permanent feature of the story. Still, within its heat and darkness, the conditions for life quietly assembled. Long before anything living existed, the raw materials and processes life would eventually require were already gathering across a violent, unwitnessed world. Liquid water pooled in early basins. Carbon and other essential elements arrived from space and formed within the planet itself, and warmth from both the sun and Earth's interior kept chemistry active rather than frozen still. None of this guaranteed life would follow. and scientists still debate exactly how the leap from chemistry to biology occurred. Yet, by the eon's final stretch, the ingredients were present together in the same place at the same time, patiently arranged by forces with no awareness of what they were building. Where a kitchen holds ingredients long before any meal is cooked, this planet held its ingredients for hundreds of millions of years before anything used them. To imagine this earliest Earth is to imagine a world already leaning, quietly and unknowingly, toward the first spark of something alive. The stage was set long before anyone arrived to notice, and so we drift to the end of our quiet journey through the Hadean, Earth's first 500 million years. From a sky glowing with frequent incoming fireballs, to a young sun burning fainter than the one that warms us now, to a hidden ocean vent releasing mineral-rich water into cooler seas above. This was a world built in darkness, without witness and without name. This world teaches us something gentle about beginnings. Nothing arrives finished. The elements that would one day become breath and bone and thought spent hundreds of millions of years simply gathering, unhurried, unaware of what they were assembling toward. There was no plan in it, and no one watching to hope for one. There was only time and chemistry and the patient work of a planet cooling into itself. Imagine standing on a shore that does not yet exist, where the water is warm and dark and utterly alone. Imagine the sky above that shore, lit not by stars we would recognize, but by streaks of falling stone, arriving one after another out of a silence with no one to break it. Imagine the inside of the earth itself, glowing faintly through thin new crust, offering up its heat to an ocean that has nothing yet to warm. This is the comfort of science told slowly, that the world is stranger, richer, and more patient than we can ever fully see, and that even its most violent beginnings were in their own way a kind of quiet preparation. If you enjoyed this quiet journey into the deep past, feel free to like and subscribe or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing more you need to do. You can allow the story of the Hadean to fade like the last light of day, leaving only calmness behind. If sleep comes, let it carry you gently. If you are still awake, you are welcome to stay, to listen again, or to let the next video continue your voyage into the quiet wonders of the deep past. Rest well, and remember, long before there was anyone to notice, this world was already leaning, quietly and unknowingly, toward the first spark of something alive. Good night.